All right, so summative 9 tomorrow is going to cover 2.4, 2.5a, 2.5b, and 2.6. So 2.4 and 2.5a are repeaters, and then 2.5b is solving rationals, and rational operations also. That's a new one. And then 2.6 is the weird inequality stuff where, like, is it a positive function? Is it a negative function? And we did some graphing and some algebra work. It was a good time. Okay, so repeated section. If you want to look back at your last summative, I think that would be brilliant at some point to see, whoops, what mistakes you made the first time and don't do them again. But this first question says they want you to list out all the possible rational zeros. So that's that theorem where you take, that's the theorem where you take the coefficient of the lead term and then the constant coefficient, and you set up a ratio of all the factors. So this is obnoxious. 52. Oh boy. All right. Let's start with 52. 1 and 52. 2 and 26. 3 and 14? 13? Is 4 and 13. Is it 4 and 13? 3 and nothing? I'm making that up. Okay, ignore me. 4 and 13. And did we get them all? 52 is a weird one. That one always stumps me. Alright, so those are going to be all the possibilities for your numerators. Your denominators could be any factor of the lead coefficient, which would be a 2. Well, that's not too bad. 1 and 2. And then the important part that some of you forgot last time was is plus and minus in front of all these that we're about to write down. So I will let you kind of shorthand it to just say plus and minus in front, but now you have to list out all of the things. So write kind of small because you don't have a lot of space here. 1, 2, 4, 13, 26, 52. That would be all of these red things divided by 1. And now we got to go through and divide them all by 2. However, you're going to notice not a lot of these have to be written down when divided by 2 because they already are written down. So like 1/2, yes. 2 halves I don't need to write down. 4 halves I don't need to write down. 13 halves, yes. 26 halves, no. And 52 halves, no. So these are all the possible rational zeros. So then what they want you to do is use your calculator to give me a little help, because otherwise I'd have to do a lot of testing, and no thank you. So could you please investigate this polynomial on your calculator? And I'm hoping you guys can find 2 places where it obviously is going to cross the x-axis. Alright, so this is a good example of why the rational root theorem is important. So we already wrote down what are possibilities for rational roots. And a lot of kids are looking at this one and thinking they have one at negative 3.5. Well, that would be negative 7 halves. Is that one of the possible roots that you wrote down? No. So don't even bother thinking that's negative 3.5 because that's not a possibility. So ignore that one, but this one, I'm pretty sure it's negative 2. I'm going to justify it by hitting trace negative 2. Yep. And then I'm pretty sure that's a 1, but let's try. Okay. Good. So negative 2 and 1 are 2 rational roots that we can use in successive synthetic divisions. That'll knock us down from a quartic to a quadratic, and that's all you really need to do. And that's what we suggest you do, by the way. Sometimes you guys get questions where you can see all 4 roots, and then you kind of get in trouble on the next part of the question. So let's not do it that way. All right, your choice. Which 0 do you want to use first? Negative 2? Okay. Don't use 2. Alright, so negative 2 is our first successive synthetic division. So you start by bringing down the 2, and then it's a series of multiply adds. So 2 times negative 2 is negative 4. 2 plus negative 4 is negative 2. Now what should my remainder come out to here? Better be 0. Let's see, that's negative 26. Times negative 2 is positive 52. Adding those up, you get 26. And then, yep, good job. This does come out to negative 52, which means the remainder is 0, which is what we needed. So ignore this part, guys. That's not going to be part of our next division. That's the remainder. We're going to go again with the other x-intercept that you guys found. Where was the other x-intercept? Positive 1? I don't know why I'm writing negative. It's positive 1. All right, keep going with your smaller cubic polynomial this time. All right, 2 times 2 times 1. Why do I keep wanting to make that negative? 2 times 1 is 2. And then those add up to nothing. 0 times 1 is nothing. Negative 26 plus 0 is negative 26. And then negative 26 times 1 is 26. And again, we get a remainder of 0, which is what we're supposed to get, so that's good. Ignore that remainder. It's not going to be part of my work. But here's what we have left. We have, remember, we started at quartic. You knocked it down 2 levels, so you have a quadratic right now. So somewhere in my work, I need to write down 2x squared. There's no x's, and then minus 26. They're going to want me to solve that, because it does say find all 4 exact zeros here. So if you were to solve this quadratic, most people would add the 26 and then divide by 2. So get x squared equals 13. And then you are going to get 2 zeros here, guys. You're going to get positive and negative 13, square root of 13, excuse me. But that's only 2 zeros, and you're supposed to find 4. Where are the other 2? Yeah, the ones we stole from the calculator, so negative 2 and positive 1. So there's your 4 exact zeros, no decimals. Can't use your calculator's trace key to do this. Then it wants you to write in factored form, maybe irreducible factors or linear factors, but must be equivalent to f of x. So here's what I would like you guys to do, just to kind of stay consistent with our work. You guys have the 4 zeros, so just, okay, 2 ways. Remember this guy? That was the remaining piece. So if you want to call that a factor right now, I would accept that. So if you called this factor of 2x squared minus 26, I'm okay with that. Now the other factors come from the zeros that we stole from the calculator. So a 0 at 1 would be a factor of x minus 1. And then a 0 at negative 2 would be a factor of x plus 2. So this one's kind of weird because of the instructions. It says maybe irreducible factors or linear factors. A little bit of a debate on whether this one's irreducible. So some of you who really just love factoring like I do say that's not irreducible, meaning I can factor it. So some of you are going to take the 2 out, and then you're also going to factor the x squared minus 13. You're going to factor it into x plus square root of 13 times x minus square root of 13. And I am totally okay with that. Technically, this 2 can be anywhere in your problem. You just can't have it multiple places. So, like, don't have the 2 distributed into, like, 2 different factors, because if you distribute 2 2's, you're really doing a 4. All right, here's the last thing I want you to double check, guys. The original problem had a coefficient of what for the lead term? 2. Does your problem that you just wrote down have a coefficient of 2 as well? Yes, because here's what's happening to some of you. Some of you take this step right here, and you go and you write all those 4 zeros as factors, which is a great plan. This is not it's not a wrong way to do this question, right? So you'll say x plus square root of 13, x minus square root of 13, x minus 1, and x plus 2. But what's wrong with this as a final answer? At some point in your algebra, and in fact I can point it out to you right here, you lost your coefficient of 2 because you divided by a 2 in the equation setup. Well, because this is not like an equation, it's a function, you can't just magically lose 2's like that. So if you do that technique where you take your zeros and you write them as factors, you just got to come back at the end and throw a 2 on the front of it, just like that. That's fine. All right. So if you're curious, okay, like what answer does she want? Like, these are obviously the same answer. This is my favorite answer. Okay. So up to you. The important thing there is not to lose your coefficient. Let's take a look at worksheet 17B. If you have already turned in your homework check, sorry about that. You can look at it up here. This is practicing graphing a rational function, and you're going to be able to use the card with all the steps on it, and I will give you a fresh one to use during your testing like we did last time. So the first step is to factor everything. So we're going to take this numerator. Obviously that's pretty factorable. So that goes into what? X minus 3 times x plus 1. And then your denominator factors, you could take an x out of that. So x times x minus 3. Uh-oh. Oh boy, we have one of those ones with a removable discontinuity. So, I'm not going to remove it quite yet, but I am going to note that we do have what we call a whole or removable, what is this doing? Discontinuity in this rational. The first question, though, they're going to want you to identify on some of these questions is like, what's the domain? Remember, the domain would be anything that would be a discontinuity, whether it's a vertical asymptote or a whole. So you look at your denominator, and you tell me what x cannot be. So x cannot be 0, or what else can x not be? 3. Now, they want to, because you're going to be graphing this one, you're going to have to identify the location of the whole next, which is the next thing on our card. So last time we tested this, a few of you had trouble with the x value for the whole. It's not negative 3. Remember, it's the solution to this factor. So the x value for the whole is actually going to be at x equals positive 3. And then to find the y value, you got to go to the reduced version. So now this is a time where you can remove the discontinuity, and you're left with x plus 1 over x. So if you were to plug in a 3 right here and right there, you get 4 over 3. Vertical asymptote would be next. So we already removed this discontinuity, which means the remaining factor in your denominator is the factor for the vertical asymptote. So remember, guys, this is a line. I want you to write down x equals 0. And then horizontal asymptote, you can go back to the original if you prefer. Is this top heavy, bottom heavy, or equal weight? It's equal weight. So if it's an equal weight rational, that means your horizontal asymptote is at y equals whatever the lead coefficients were. So y equals 1 over 1, so y equals 1. And then it's not top heavy, so you don't have to worry about oblique. So if I was graphing this, I would take a highlighter, and I would graph, oh boy, yuck, the vertical asymptote at 0, the horizontal asymptote at 1. I'm going to make a ridiculously exaggerated open circle at 3, 4/3. So 3, 4/3, remember 4/3 is like 1.3 repeating. So totally like right here. The open circle takes up the entire block, but whatever, you get the idea. And then from here, oh, you know what I forgot to find? X-intercepts, goofy me. Alright, there was an x-intercept and a y-intercept. Well, we'll talk about the y-intercept, but let's talk about the x-intercept first. X-intercept at -1. And then for a y-intercept, that would be where you plug in 0 for all your x's. So if you go back to the reduced or the original one, you're going to end up with -3 divided by 0. So what do you tell me about the fact that there is no y-intercept? Which makes sense, guys, because if the x-axis, sorry, if the y-axis, no, if the x-axis, oh my gosh, if x equals 0, see, coffee. If x equals 0, if there's a vertical asymptote there, you can't have a point there. Do I have a point? I don't know. All right, none. There's none. Graph. Ugh. Now, when you guys are graphing this, you can graph. I would suggest you graph the original version. Just remember, you have parentheses around the numerator and around the denominator. And I'm guessing it looks like this. But who knows? Close? I mean, I know it looks like a toddler drew it, but close? Close. Okay. Next, if you have worksheet 15B handy, you might want to check that one out. So, this one, I don't think they want me to actually graph anything. They just want me to find stuff. So these are the types of questions we saw in our no calculator test, but they're all good examples of what to study for. Now, guys, we are going to get a little tight on time here. Is there anything in particular you want me to go over? We kind of just already did this. This one's not even top heavy, so there's no oblique on it. Any particular part of that you want me to find again? Okay. This is another find the whole. So make sure when you guys are factoring, and you're going to get x plus 5, x minus 5 over x plus 5 times x plus 2. Make sure that when you notice, oh, that's a plus, gosh. When you notice that there's a removable discontinuity because of the factor x plus 5 over x plus 5, what is the x value for that whole? It's negative 5. Thank you, thank you, thank you. And then you're going to remove it before you plug it into the function to find the y value. Okay, what do they want when it says n behavior asymptote? What is that code for? It's the horizontal asymptote, and you're going to have to do division. So, oh no, I'm lying. Ignore me. Gosh. Why do we not have to do division on that one, people? Because it's equal weight. Is there one where we do division? Yeah, right there. That's the one. All right, and behavior equation. That's fancy talk for the horizontal asymptote, or if it doesn't have one, the oblique asymptote. So since this one is top heavy, won't have a horizontal asymptote, but will have an oblique asymptote. Okay, I don't know if I can make it the whole day without coffee. I'm going to be honest, guys. This is rough. All right, here we go. Long division or synthetic division. What do you want? That was a quick synthetic. Okay. What goes in the little box here is the solution to your divisor, so 6. Please be careful, guys. You are missing a term in here. Do you see how there's no quadratic? And then don't forget, for the oblique asymptote, for the end behavior equation, you don't really care about the remainder. It can come out to whatever. I just don't need it for part of my answer. So we have 6, 36, 32. Oh, I don't really care what that is because that's the remainder. Did I even do that part right? That was a really quick mental math on a Monday. Okay, so your end behavior equation is, make sure you have a y equals in front of this. X squared plus 6x plus 32. No, I didn't finish the question, but I don't care. All right. You guys did really nice on that question on the no calculator test where you had to create an equation that had certain attributes. Nice job. Keep it up, children. All right. 2.5b. What is this business? All right. So we're still on our review, or we're back to our review. And the first part of 2.5b is going to have you do rational operations. So adding, subtracting, multiplying, dividing. Adding and subtracting is the one where you have to get common denominators. Multiplying and dividing shouldn't be too tricky as long as you're a fine factorer. So the first question is a subtraction question, which means we need common denominators. So your common denominator would be an m plus 1 and an m plus 5. So now you have to go build up the common denominator. This first fraction needs an m plus 5. Ooh, that's ugly. And then this denominator needs the m plus 1. So you don't have to do any work on the denominator. It's already written. I want you to keep it in factored form. But up in this numerator, got a hot little mess here. All right, 6m times m plus 5 is 6m squared plus 30m. And then be careful, guys. This is a negative 2m that you're distributing to m plus 1. So that's negative 2m squared. And then minus 2m. That right there is the most common mistake as a child, not distributing the negative all the way through. So then that blue numerator, we'd like to collect our like terms. So you have a 4m squared plus 28m. And then I do notice that's factorable. But when I go to factor it, I kind of mentally, I would take out a 4m and have m plus 7 left over. None of that's going to cancel, so this is actually a great answer, but I think you all have traumatic memories from Algebra 2 where they snuck that question in at the end, where like you had to factor and cancel right at the end. So always watch out for that extra factoring, especially if you're notorious for not coming up with the least common denominator. Those of you who just build a common denominator that's not always the least one, you usually end up with extra factors in your numerator that you have to cancel out later, so watch out for that. Okay, the next question is division, but we don't actually divide fractions. What do? We change it to a multiplication sign by reversing the second fraction. So I'm going to kind of factor and flip all at the same time. This numerator looks like we'd factor out a 9x. And then this denominator is just a traditional trinomial, so x minus 8 and x minus 5. We've changed this to a multiplication problem because we're going to flip. So this now becomes my numerator. Take out a 5x squared, x minus 1. And then boring little denominator of 9x. So multiplication questions, while they look like two different numbers, two fractions, they're really just one big fraction. This is my favorite part. You get to cancel things. 9x's are gone. What else? X minus 5's are gone. So that's all you can cancel. The 5x squared times the x minus 1, I would leave it in factored form, over the x minus 8. And you'll notice that I often keep my binomial factors in parentheses as well. That just kind of stops kids from doing crazy canceling at the end. So use that little trick if you want. Okay, on the back. 2.5a or 2.5b is also solving. So these are equal signs in the middle, which means you get to do whatever you want to the equation as long as you do it to everything. So you have to find a least common multiple for your denominators, and it is best if you shoot for the least common multiple. So I have an a, 3a, and an a. What would work? I think we just need a 3a, yeah. So this gets distributed, 3a over 1, to every single term, meaning every single fraction. And this is all one gigantic term here. And you can write a 3a in front of each fraction. Like if you get a little tripped up on this step, do that and maybe write it in a red pen. And then you can simplify each, we talked about bubbles. We put bubbles around them before. I'm just going to shorthand it though because we're almost out of time. 3a times 4 over a, the a's will cancel. And you're still left with 3 times 4, better known as 12. Now the second fraction, 3 and a will cancel. So you're still going to have an a squared plus 4a minus 12. Oop, I forgot to do my first step. I'll come back to that. And then 3a times that last fraction, the a's will cancel, so it's 1 times 3, so you have a 3. I kind of forgot to do the step though, guys. Tell me what a cannot be. Yeah, a can't be 0, so just keep that in mind as we get to the end of this question. All right, we do have a quadratic. I'm going to subtract 12 over. Now be careful, these 12s are not canceling. There's also a 3 here. So you get 0 equals a squared. Plus 4a. Minus 24 plus minus 21. And then we're factoring, and this is a case where I think we get two solutions and they both work. So a plus 7 times a minus 3 will be a good factorization. And then don't forget to take that last step, guys, of actually solving. So a is negative 7 and a is 3. Neither of which were my excluded values, so we get to keep both. Guys, notice the 3 was like a numerical coefficient, not a factor necessarily that would produce a divide by 0. Oh boy. All right, this one, the denominator here and here are not in their best form, so we need to factor them. So let's factor out, let's see, a common a squared. Pen, where you at, buddy? There you go. So you have a plus 5 times a squared. Same thing over here. So ignore that. Now when you think about putting big parentheses outside of this, around this equation and then putting an LCM outside of it, the least common multiple, I need to get rid of an a squared and an a plus 5. So that's going to get multiplied to every single term, and math is in your favor on this question, guys, because the first and last fraction, the entire LCM and the entire denominator will cancel each other, so that's wonderful. You just have an a squared minus, oh, I did it again. I forgot to write the excluded values. We'll come back. All right, a squared minus 8a plus 16. Now be careful in this middle fraction. When you multiply the LCM times this middle fraction here, the a squareds will cancel, but you still have an a minus 3 times an a plus 5 quantity. So you have the quantity a minus 3 that still has to be multiplied by the quantity a plus 5. Now the last fraction's nice and easy. They're going to cancel, you just get a 1. This is the part I'm concerned about right here. And if there happens to be a coefficient in addition to the factors of binomials, remember in that case you need to kind of do it in 2 stages. You got to FOIL out the binomials and then distribute the coefficient. All right, so here we get, what, a squared plus 2a minus 15. And of course it's a quadratic. All right. Since I keep forgetting to do it, can you tell me what a can't be? Can't be 0. And can't be -5. So keep those numbers in mind in a minute. All right, guys, let's look at our quadratic. We have 2a squareds. Minus 6a. Plus, minus. Oh, but then you're going to subtract the 1 over it. Don't you get a 0 there? Okay, so this is your quadratic. It's not nearly as impressive as I thought it was. All right, let's factor out a common factor of 2a. So 2a times a minus 3. Okay, okay. Look at this. A equals 0. We'll talk about that in a minute. A equals 3. So let's back up to like 45 seconds ago. You just told me a can't be 0. It's excluded, and a can't be -5. So you are going to cross off a equals 0, tell me it's extraneous, and the only viable answer is a equals 3. That was fun. All right. Definition of fun is weird. 2.6. Oh boy. So this is the one where we kind of took a hybrid approach with the graphing and the sign chart. So when it's a polynomial like this, you don't have to do any work other than make sure it's in standard form. So go ahead and graph this guy into y1. However, I will tell you that every polynomial I'm going to give you is probably factorable. So just to kind of like have your algebra match your graphing, I think it's always a safe bet to go and take an algebraic approach. So like you could factor an x out of this, and then you could factor further. So x minus 7 and x plus 1. So according to my algebra, you guys should be finding x-intercepts at 0, 7, and -1. Are you seeing that? Not in that order, obviously. It's in number line order. So this is where I think some of you might want to go ahead and do a sign chart, even if you don't think you need it, just because I think it helps with domain intervals. So in number line order, -1, then 0, and then a 7. And I want to know where your function is greater than or equal to 0. We'll get to that in a second. So starting before it hits -1, is it positive or negative? Is it above the x-axis or below the x-axis? Before -1? It's below, isn't it? It's negative? Okay. And then how about between -1 and 0? Positive, okay. And then how about between 0 and 7? Negative, okay. And there's no bounces in this one, so it should toggle between the two. So let me guess, this one's positive? Okay. So the domain of where your function is greater than or equal to 0 would be where your function is positive. That's code word for positive. But also including a 0. So you're going to see some brackets here, guys. So it starts its positive life right here. And then it still is positive or greater than or equal to 0 right there. Picks up again at 7. And then it's going to go to infinity. So notice I used brackets even on my sign chart because my interval starts at -1, goes to 0, union, starts at 7 again, and goes to infinity. Okay, someone tell me in not my words, why did I just use brackets on -1, 0, and 7? Because the symbol says greater than or equal to 0, and at those values the function is exactly equal to 0. Those are zeros. Okay. So that's what a hybrid approach looks like, guys. We're kind of graphing it. We're kind of using a sign chart. It's the best of both worlds, I think. Whatever. All right, the next question is not a polynomial. This is a rational. And remember, we just have to make sure everything's to one side. This is the version that you're going to put in your calculator. Just watch how you're typing it, guys. Make sure that your denominators, if they have more than one thing in them, have parentheses. But that's not the version that I'm going to confirm with algebraically, because that's not general form. So while you guys are typing that in your calculator, I'm also going to work towards getting some common denominators. So, common denominator here would be a 7 and an x plus 3. That's kind of weird. So this one's going to be hit by a 7. And then this one's going to be hit by an x plus 3. So this numerator is 7 times 5, so 35. Careful here, guys. It's a subtraction of 2 times an x plus 3 quantity. So it's negative 2x minus 6. Alright, so finally cleaning this all up, what do we have? Negative 2x, oh goodness, plus 29? Did I add right today? You guys are looking at me like I know what I'm doing. Did I not tell you about my coffee problem? Okay. So, according to my algebraic calculations, remember, you're supposed to set numerator and denominator equal to 0 because a place where your rational function could change sign would be at a vertical asymptote or at an x-intercept or a hole, technically, but not really. We'll talk about just setting the numerator and denominator equal to 0 and you telling me some problems that I should be seeing on my calculator. So this is kind of a weird one. You have a problem, an x-intercept, if you will, at, okay, negative divided by negative, positive, no, yes, positive 29 over 2, which is 14.5. Is that, can you see that on your calculator? Not probably in the window you're looking at, so could you extend your window back a little bit and confirm for me that it does cross the x-axis at apparently negative, positive. I already forgot what I said. Positive? Positive. Positive 14.5 or 29 over 2. We're going with yes. Okay. Okay, and then according to the algebra, there also should be a vertical asymptote right here at x equals negative 3. Do you see a vertical asymptote at x equals negative 3? Excellent. Okay, so negative 3 would come before the x-intercept of 14.5. If you want to call that 29 over 2, that's fine. Now, y'all are looking at the picture, and you just confirmed for me the x-intercept and the vertical asymptote, so I'm feeling like we did some good algebra work. So I'm going to trust your picture here to help me fill out the sign chart. Before it was at the vertical asymptote at negative 3, was your function positive or negative? Was it above the x-axis or below the x-axis? Below, okay, so it's negative right here. Now between the vertical asymptote and then the place where it hits the x-axis, the intercept. Positive? Okay. And then it goes through the x-axis, wow. And then it goes back to negative. Okay, now we have to make a little note, guys. This one right here, this is an asymptote. This one's an x-intercept. And that's super important in this last step here. Because they want to know when your function is less than 0. So in this case, it doesn't really matter. We're going to be using parentheses on everything. But if they put a less than or equal to bar on that, you have to remember that equal to 0 is okay for x-intercepts, but it's not okay for asymptotes. You will never get to the asymptote. That is why it's a discontinuity. So keep that in mind if you ever have an equal to 0 on these rational ones. Anywho, they want to know where it's less than 0. That's fancy talk for negative. So we're looking here to here and here to here. So we go negative infinity to negative 3. And then union, I don't care what you call this, 29 halves. You can go to 14.5 if you want, 29 halves to infinity. So one thing I will say about the weird looking sign chart, it's really nice for coming up with domain intervals. Really nice. All right, good luck.